Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about a module Overview of Nuclear Fuel Materials Part 1 from paper Energy Related Materials. So students, let us see what we are going to learn from this module. From this module, you may get to know about the following. First, meaning of nuclear fuel. Second, materials available as nuclear fuel for nuclear reactors. Third, current scenario of uranium fuel and the methods of its like mining, milling, fabrication and enrichment. Lastly, the important properties of uranium as a nuclear fuel. So students, let us start with a brief introduction of nuclear fuel materials. Amongst different components of nuclear reactor, the reactor core, which is also known as the heart of the reactor, contains nuclear fuels. A nuclear fuel is a radioactive material that is used to generate nuclear fission reaction, which produces huge amount of energy, basically heat energy, that is utilized to generate electrical power under appropriate conditions. The requirement of nuclear fuel are discussed in detail as follows. In order to maintain the cost effectiveness of power production, the cost of the fuel must be minimum. Secondly, nuclear materials should have high value to thermal conductivity to ensure that they can tolerate the thermal gradients produced between the fuel center and edge. Thirdly, nuclear fuel materials must be able to resist repetitive thermal cycling due to the reactor's on and off condition. Nuclear fuel must have high corrosion resistance towards reactor fluids. Next, the fuel should be free from any kind of defect with neutron capture cross section to facilitate the adequate neutron economy. Another one is that the fuel should have high mechanical strength to sustain mechanical stresses. The fuels must be recyclable and or disposable. There are majority of materials which can be used as nuclear fuels in nuclear reactors, including metal or alloys like uranium, plutonium and thorium, and ceramics like oxides, carbides, nitrides and silicides compounds. These materials are fabricated as nuclear fuels in various configurations, such as cylindrical pellets in the form of rods, spherical particles, coated particles, and in the form of a fluid. Let us define some important basic terms regarding nuclear fuels before we begin with the nuclear fuel. First, burn up. Fuel burn up is an important characteristic of nuclear fuels, which is defined as the quantity of heavy metal in the nuclear fuel that has been fissioned. This term is generally presented as a percentage of heavy metal atoms that have been fissioned, or as fission energy gigawatt day. 1 gigawatt day, or GWD, is equal to 8.64 multiplied by 10 to the power 13 MWD produced per metric ton of the heavy metal. Second is blanket fuel. It is defined as the reactor fuel that contains the fertile isotopes, which are bred into fissile isotopes. Next is driver fuel. It is defined as the reactor fuel that contains the fissile isotopes along with fertile isotopes, which are bred into fissile isotopes. Next, we will discuss the reproduction factor, or RF. It is defined as the number of neutrons, or eta, generated per neutron absorbed in a fuel. If number of neutrons are produced per fission reaction are nu, and the number ratio of fission to absorption in fuel is sigma F divided by sigma A, then reproduction factor can be defined as follows. Eta is equal to sigma F by sigma A multiplied by nu. The value of eta is higher for fast reactor in comparison to thermal reactors. Next is conversion ratio, or CR. It is defined as the ability of a nuclear reactor to convert fertile isotopes into fissile isotopes and can be written as follows. That is, CR is equal to fissile atoms produced divided by fissile atoms consumed. When CR is greater than 1, it is called as breeding ratio, or BR, that generally found in case of fast reactors. Next is fission products, or FP. Product nuclei resulting either from the fission of heavy elements such as uranium or the radioactive decay of those primary daughters. The fission products can be classified as follows: fission gases and other volatile elements such as Br, krypton, Rb, I, xenon, cesium, and tellurium. Next is FP forming precipitates like molybdenum, Tc, ruthenium, Rh, palladium, silver, cadmium, indium, tin, antimony, selenium, tellurium. Next is FP forming oxide precipitates Rb, strontium, zirconium, niobium, molybdenum, antimony, tellurium, cesium, and barium. Last is Fp dissolved as oxides in fuel matrix. Rb, strontium, zirconium, niobium, lanthanum, cerium, Pr, Nd, Pm, Sm and Eu. Last is Fisium or Fs. It is nominally 2.4 weight% molybdenum, 1.9 weight% Ru, 0.3% weight% Rh, 0.2 weight% palladium, 0.1 weight% zirconium, and 0.01 weight% niobium, and is designed in such a way that it can mimic noble metal fission products, remaining after a simple reprocessing technique based on melt refinement. Nuclear fuel materials. In this slide, we will be discussing about various metallic fuel materials. The metallic fuel contains materials such as uranium, thorium, plutonium. U and plutonium based fuels were primarily used in EBR first in 1951 to produce suitable amount of electricity. Further, EBR2, Magnox, and various other fast reactors have also utilized metallic fuels. However, the water-cooled reactors avoid the use of metallic fuels because of the compatibility issues between water and metallic fuel. As at higher temperatures, the metal fuels could form metal hybrids or oxides. Nuclear fuels based on metal oxides were chosen by designer in place of metallic fuels, as they proposed that metallic fuels would have only limited burn-ups because of the apparent swelling issues and expected formation of liquid phases in fuels during the higher temperature processes. At that time, metal oxide fuels were suggested for reactors, even though only less information was available on them. After few years, the changes in fuel elements design opened the gap between the nuclear fuels and cladding materials that gives a plenum volume for gathering fission gases and presented significant improvement 1% versus 20% burn up over the earlier designs. However, it is noteworthy that research and test reactors have generally used metallic fuels, mostly due to their low operation temperature. Here we will discuss about three major metallic nuclear fuel materials, that is uranium, plutonium and thorium. The fuel materials have various advantages as well as disadvantages over often specific to the type of fuel. Advantages of metallic fuel is they have high thermal conductivity, high fissile atomic density, and excellent fabricability, while lower melting points, irradiation instabilities, corrosive nature in reactor fluids, and several compatibility problems with the fuel cladding materials are the main disadvantages of metallic fuel. However, metallic fuels in the form of alloys can significantly enhance their corrosion resistance. Now, students, we will be discussing about uranium. Uranium is the most abundant material that has atomic number of 92 and contains a part of about 4 ppm parts per million of the Earth's crust. The estimated amount of economically recoverable uranium was about 5.5 million tons as estimated in 2007. Majority of uranium may be extracted from the Earth's crust is called as natural uranium, which contains 238U around 99.28%, 235U around 0.71%, and 236U around, which is very much less than, that is around 0.006%. Uranium is generally found in the form of uranium oxide such as triuranium octaoxide and uranium oxide, followed by carnotite. Uranium minerals of high grade are mainly extracted in Kazakhstan, Canada, Australia, Namibia, South Africa, Niger, and some parts of United States, and so on. As per the estimated made in or estimation which has been made in 2010, Kazakhstan is the world's leading country for uranium production, that is around 27%, followed by Canada, which is around 20%, and Australia around 20%. However, substantial amount of uranium can also produce by recycling the spent fuels collected from nuclear reactor. However, there are laws which prevents the recycling of these spent nuclear fuels in the United States. Hence, most of the commercial uranium fuels in US are being used after extraction from the minerals. But France, which utilizes recycled spent fuels for satisfying the fuel requirements. Now we will discuss about the sources, extraction, and preparation of uranium. Uranium is basically found in Congo, Canada, US, Africa, Ukraine, and everywhere to some extent. For many decades, several methods have been pursued for mining of uranium. Majority of uranium minerals available in the earth crust contains varieties of impurity materials which are essential to separate from the mineral with a metallic value. Hence, the uranium extraction technique includes mineral beneficiation process of removing gang of impurity particles to enhance the metal value of the uranium mineral by removing the impurity materials. Generally, the uranium mining is accomplished through chemical methods as physical beneficiation processes are not that effective to release ore minerals of value. Here, few common techniques for uranium extraction are discussed in detail. In order to recover maximum content of metallic uranium, it becomes essential to use leaching reactions of raw ore. The leaching is the process of extracting uranium from raw ore by reacting ground uranium ores with dilute acids such as sulfuric acid, nitric acid, and hydrochloric acid. Sometimes sodium carbonate is also used as a leaching agent under certain conditions. However, the ore most often pass through preliminary treatments such as roasting and grinding prior to leaching, which burns carbonaceous species confined within the ore that makes ore more reactive for leaching treatments. Sometimes the ore is roasted with salts to improve the solubility of impurity metals such as vanadium in the leach solution. Although the accurate details of the pre-treatment procedure are determined by the conditions of the mined uranium, the leaching process is carried out by using either an alkaline or acid leaching agent, the choice of which is ultimately determined by the economics of the procedure, which depends on the nature of the ore. It is important to note that acid leaching avails higher recovery of metallic uranium than alkaline leaching. However, acidic leaching has some limitations as it cannot be used for ores that contain magnesium or calcium carbonates because these compounds have a tendency to react with acid leaching agents, which result in the wastage of an excessive amount of acid. Additionally, due to the issue of corrosion, the tools and technique used in acid leaching are far more expensive than alkaline leaching, as corrosion problems are not so severe in alkaline leaching. However, the main disadvantage of alkali leaching is their unsuitability of leaching ores containing gypsum, sulfide, and refractory constituent. Another important stage after leaching is done is the recovery of metallic uranium from the leach solution, which can be accomplished by the methods including chemical precipitation, ion exchange, and solvent extraction. Amongst them, ion exchange is the most common method used for the recovery of metallic uranium after leaching by sulfuric acid. Ion exchange method uranyl sulfate ions can be removed selectively by letting them to be adsorbed on ion exchange resin, after which the adsorbed ions could be detached from the resin with a solution concentrated with nitrate or chloride ions. Through this process, a yellow powder containing 80 to 85% of UO2 can be achieved. This yellow powder is filtered after dissolving in nitric acid that produced uranyl nitrate, which can be extracted with the help of ether. After that, the filtrate is washed with water several times to produce an aqueous solution. From there, Pure ammonium diurenate can be precipitated by passing ammonia gas to separate diurenate. The diurenate is then dried and reduced to uranium dioxide in hydrogen at 650 degrees Celsius. The ammonium diurenate can also be converted to uranium trioxide by heating that removes ammonia and vapor, after which uranium trioxide is treated with hydrogen at approximately 600 degrees Celsius to create uranium dioxide. Next step is to convert and the enrichment of uranium. The amount uranium oxide achieved after uranium milling practically not usable as a nuclear fuel for a nuclear reactor. Thus, it requires additional processing. It is noteworthy that 0.7% of natural uranium is capable of undergoing fission or fissile in nature, and it is found in the form of 235U, and the remainder is uranium 238U. Hence, for better fuel quality for several nuclear reactors, the concentration of the fissile isotope needs to be increased, that is, typically to be between 3.5% and 5% of 235U. Enrichment is the physical process to increase the concentration of isotopes which require the uranium to be in a gaseous form. In this process, the uranium oxide concentrate is first converted to uranium hexafluoride ready for enrichment plant. After that, uranium hexafluoride is then sapped into 14-ton cylinders where it solidifies and shipped to the enrichment plant. In enrichment plant, the gaseous uranium hexafluoride gets separated into two streams by enrichment process, where one enriched to the required level and is known as low enriched uranium, and the other stream is progressively depleted in 235U and is called as tails or simply depleted uranium. Majority of enrichment process in commercial plants uses centrifuges with high RPM values for vertical tube, where the physical properties of molecules separate them due to high spin. Finally, they are allowed to laser enrichment process, and the product of this stage is called as enriched uranium hexafluoride, which is reconverted to produce enriched uranium oxide. Up to this point, the fuel material can be considered fungible. Finally, let us discuss about the fabrication of uranium. The nuclear in nuclear reactor is generally supplied in the form of ceramic pellets, which are prepared from uranium oxide sintered at a high temperature of about 1400 degrees Celsius. The fuel pellets are covered in strong metal tubes to produce fuel rods, which are organized into a fuel assembly ready for place into a nuclear reactor. The size or dimensions of the fuel pellets and other parts of the fuel assembly are accurately controlled to ensure the steadiness in nature of the nuclear fuel. The size and the shape of processing vessels are taken very precisely with great care to avoid criticality of limited chain reaction releasing radiation. However, Fuel criticality is unlikely with low enriched fuel, but it highly considerable for the plants handling special fuels for research reactors. Some 27 tons of fresh enriched fuel is required each year by a 1000 megawatt reactor. Further, the fabrication of uranium is decided by various factors such as its reaction affinity with air and hydrogen and anisotropic properties. However, various techniques including rolling, forging, casting, extrusion, swagging, wire and tube drawing, machining, and powder metallurgy can be used for the fabrication of uranium. Now let us discuss about the physical properties of uranium and a little bit discussion about its crystal structure. In spite of being a metal, uranium has features of chemical bonding of metalloids such as arsenic, antimony, or bismuth. The crystal structure of uranium changes for various temperature ranges. Up to a temperature range of 666 degrees Celsius, it adopts an orthorhombic crystal structure, that is alpha U, which has 4 atoms per unit cell, 19.04 gram per centimeter cube of density, and lattice constant of around 2.8541 plus minus 0.003 Armstrong, and B equal to 5.8692 plus minus 0.0015 Armstrong, and C equal to 4.9563 plus minus 0.0004 Armstrong. The structure can be described as a stacks of corrugated sheets with atoms arranged parallel to AC plane with an atomic separation of around 2.8 Armstrong within the sheets, where the sheets are separated by a distance of around 3.3 Armstrong. This structure can be defined as distorted hexagonal close-packed structure. Within the temperature of 666 to 771 degrees Celsius, it shows a complex tetragonal structure, that is beta U, which has 30 atoms per unit cell. Now, for a temperature range of 771 to 11130 means 1130 degrees Celsius, it has simple body centered cubic crystal structure denoted by gamma U, which has 2 atoms per unit cell. Due to anisotropy in crystal structure of alpha U, its properties such as thermal expansion coefficients are anomalous along the crystallographic directions. As discussed earlier, uranium displaced allotropic transformations. Hence, it shows increased volumetric thermal expansion coefficients because phase transformation takes place as a function of temperature. Further, thermal conductivity is also an important property when it comes to heat transfer mechanism in a nuclear reactor. The figure shows the variation in thermal conductivity of well annealed high purity polycrystalline uranium with temperature. It is noteworthy that the thermal conductivity of uranium keeps on increasing with increase in temperature and provides the advantage of superior heat conduction at elevated temperature. Next, we are going to discuss the mechanical properties of uranium. Pure uranium is a partially ductile material whose mechanical properties depends on crystallographic directions or texture, which is ultimately affected by the fabrication history and heat treatment. Besides this, grain size and shape also affect its mechanical properties significantly. The tensile strength and modulus are sensitive to impurities atoms such as carbon, fission products, and alloying elements. The figure shows a typical stress strain curve of the uranium, and the below table shows the tensile strength decreases precipitously with temperature. Uranium is a material which is highly prone to corrosion in most environments. So now we will be discussing the corrosion properties of uranium. So uranium gets corroded in the environments such as air, oxygen, hydrogen, water, water vapor, etc. Freshly polished surface of uranium, which has a dull silvery color, changes to straw-like color and blue-black color within few days. When it is exposed to air, the oxide films produced on its surface are not quite protective. However, at elevated temperature, the oxide film thickness increases with time, which starts cracking and exposing pure uranium metal under the oxide film. Unalloyed uranium shows highly corrosive nature in water as shown in the figure. Within 50 to 70 degrees Celsius, the originally formed uranium dioxide film protects metal uranium for a significant period of time. However, as temperature increases beyond 70 degrees Celsius, corrosion rate also increases. On the other hand, in degassed water, that means hydrogen saturated, the corrosion rates remain linear with time in the significant temperature range. It is assumed that in degassed water, hydrogen diffuses through the oxide film to form uranium hydride UH3 in between the oxide and the metal, and also into the grain boundaries of uranium, which adequately protects from the corrosion of metal uranium. Now, we will be discussing about the alloying of uranium. Alloying of uranium is generally done to improve its properties such as mechanical, dimensional, and corrosion resistance. However, the choice of alloying elements is not supposed to affect the neutron economy. Thus, the various emphasis was placed on the alloying elements such as aluminium, Be, and zirconium. The alloying materials such as titanium, zirconium, niobium, and molybdenum, they have broad solid solubility in uranium at elevated temperatures. Vanadium and chromium, they have reasonable solubility, and tantalum and tungsten, they have least solubility in gamma uranium. The alloyed uranium such as UMO, U-zirconium, and U-Pu zirconium fuels was used in EBR first, which showed significant improvement in dimensional stability under irradiation and corrosion resistance. Further, the uranium alloys based on Fissile UFS or UFZ, that is Fissile, are being used in LMFPRs. Uranium fissile are produced while reprocessing of spent fuels, in which amount of the fission products like molybdenum, niobium, zirconium, RH, and ruthenium, etc., are left in the uranium matrix. These uranium alloys shows better irradiation stability. Besides the excellent stability, alloyed uranium shows high strength at elevated high temperature strength, which is very advantageous as the strength of uranium decreases drastically at elevated temperatures. However, inclusion of large amounts of alloying materials in uranium may result in its brittle formation, which adversely affects the ductility and fabricability of the alloyed uranium. Another route of hardening the uranium alloys is its martinistic transformation. So, students, let us summarize what we have learned in this module. In this lecture, we discussed half content of the nuclear fuel materials, which covered an introductory description of nuclear fuel materials and its important characteristics. Also, this lecture covered a detailed discussion of most of the important nuclear fuel materials, that is uranium, and its various properties. Thank you.